This video looks at dynamic pricing when demand is linear in price. And this is the first of 3 videos. Again, this is linear demand. Later on, we'll take a look at a more realistic demand function, which is the log-log demand. And then the third video is a cautionary tale about what can go wrong. It's called endogeneity. And one solution to it is 2-stage least squares. Well, dynamic profit maximization is also called revenue management, and it's been around since about the 60s or so, and the airlines and hotel industry uses it quite a bit. So when you're flying on a plane, almost everyone on that plane has a different ticket price. And so their ticket price depends on when they booked the flight, okay? What kind of contract or agreement their travel agent or business had with the airline company, what the demand for the flight was, and so on. So there's all these different factors that go into the price of your airline ticket. And those prices change very rapidly over time. And so what's happened with e-commerce is that we can use the same kind of tools for pricing everything you see on Amazon. Okay, and even outside of e-commerce, if you think about Walmart, they have, about 5,000 different stores and about 100,000 SKUs, and all those things need to be priced. And one step in doing that is estimating demand. And demand estimation is one of the biggest areas of business analytics. You need demand estimates for inventory management, for supply chain management, and you also need it for marketing exercises such as pricing. Okay, so we're having a very stylistic example, and Sridevi is a college student from Traverse, Michigan, and during the summertime, she runs an ice cream stand up by the beach in Traverse, Michigan. And so she has something of a local monopoly in that the people who go to the beach and who want ice cream will go to her ice cream stand. It's unlikely that they will get in their car and travel into town to go to a shopping center to pick up some ice cream and bring it back. Okay, and she's been using dynamic pricing on a kind of ad hoc basis for a few summers, right? But she took an econ course and said, hey, I can probably use some of these tools to try to do a better job of pricing. So a little factoid is on average the variable cost of her product is $2. Okay, and so that's the variable cost, just the cost of the ice cream cone or milkshake or whatever she's selling. Here's a beautiful picture of Traverse City, and it's actually 2 bays, a very beautiful place. And so there are the 2 bays, and you can see Lake Michigan in the background. If you ever get a chance, come on out to Michigan, visit Traverse City. Okay, so here's some data, all right? And so this is past data. We have the price and then the number of units that Sridevi sold. And so this is daily demand. And not surprisingly, as the price goes up, average price goes up, demand goes down. And we have the estimated function here that the number of units is 723 minus 49 times the price. Okay. Now, price is kind of a funny thing. We have an average price. There's actually some probably variation for the different types of item. Okay, so what we want to do is, based on this estimated demand function, what will the profit look like? Well, the estimated demand function is 723 minus 49.28 times price. And we can go ahead and get a profit function out. You take price minus your variable cost, right? And so that's your margin. Price minus cost is your margin. And then you have the demand function, B0 plus B1 times X, and minus the fixed cost, right? And so in terms of the price, fixed cost is just a constant. How do you maximize price? Well, if you had calculus, right, good for you. You can do this. So you can take the first derivative profit with respect to price, X is price, and set that equal to 0 and solve it. And the optimal price, or X at, is given to you by C minus B0 over B1 divided by 2, right? And so if you use the parameters that we have estimated here, you come up with $8.34. So this minus B0, B1 is just the price where demand is equal to 0, right? So that's where this line, this red line, crosses the x-axis, and so the optimal price is halfway between the cost. The cost is $2, and then the price where demand is equal to 0. And keep in mind that the B1 is negative in this. Okay, so that's how you would do the pricing if you have this demand function. And so just a little graph of this. In this graph, we have the profit on this axis and the demand on this other axis, just so the scale works out. And so we have our linear demand, and then the profit function will be quadratic. And so quadratic functions are very easy to optimize, and there's the optimal price here. Often in economics, you see a graph like this. Again, here's your cost. Here's where we cross the x-axis, and then the optimal price is halfway in between those two, right there. And the rectangle is your profit minus your fixed cost, right? So this is your margin from 8 point whatever to $2 minus 2 is your margin, and the height is your demand. So you multiply those two together and you get your profit minus your fixed cost. You might want to ask too, what happens as the slope for price changes? And we can see that. We can go ahead and see that here in this graph. So that's just another, just the graph with the demand function, the profit function, and there's the optimal price. And we can see that as the slope gets smaller and smaller, I should say closer to 0, people are becoming less and less price sensitive, right? And when people become less and less price sensitive, you can shift your pricing up, right? You can make more money. Okay, they really want that ice cream cone because it's a real hot day, and so when that happens, you can charge more, right? And you can see that happening here with the demand functions getting flatter and flatter, and that means the profit function is moving, the profit function is moving out, and the optimal price moves out too. And if the function gets steeper and steeper, then obviously people are more price sensitive. If it's a cold, rainy day, hey, you have to charge less for your ice cream. Okay, so enough of that. So some cautions about this. Often in economics, you don't worry about statistical estimation issues, but there's some very, very big ones here. And one of the big ones is, here's your data, right? And what we have to do is project the line down to where it crosses the x-axis, right, to find out what the optimal price will be. Well, there's a lot of uncertainty in the estimate of demand at that point, right? So here are just confidence intervals, and they get wider and wider the farther you get away from the data. And so they're very wide down here. And so actually, where it crosses the x-axis could be as small as the orange line or as big as the gray line with 95% confidence, And so when you translate that back to price, you get a wide range of possible prices for this, okay? Some other estimation challenges, we never had the situation where price is actually 0. Now, the optimal price depends on the y-intercept, and usually y-intercepts are poorly estimated, right, as you can see here. And then the optimal price also depends on a ratio of two parameters, and ratios are notoriously difficult to estimate because they have high sampling variation. So ratios tend to magnify your sampling variation, which is what we can see here when we're looking at this estimate. And that feeds forward into your optimal pricing, okay? So, there's some estimation challenges there that are very important in reality, right? Because you hope this thing works in the real world, not just on PowerPoint slides. So with dynamic pricing, we're going to ask, hey, what happens if it rains? Okay, well, you probably think, hey, fewer people go to the beach, it's a little bit colder out, probably will sell less ice cream, maybe. Okay, so what we have is a dummy variable or a binary variable that indicates coding for a rainy day. It's 1 if it rains and it's 0 if it does not rain. So your data set just has a column of 1s and 0s. 1s for rainy days, 0 for sunny days. And what happens is whether it rains or not rains, it shifts demand. It shifts your demand functions up and down depending on whether it's going to rain or not. And so we can put that into the regression model. Okay, we can't just do a linear trend in an XY scatter plot, but we need to use a data analysis regression or some other package. And so here's our model. The y-intercept is 720 minus 44 minus 45 times price minus 63 times rain. So if it's a sunny day, rain is equal to 0, and you have 1 linear regression, 720 minus 45 times price. If it's a rainy day, then you're picking up the 1 here on the minus 63. And so your y-intercept becomes 657, and then it's also minus 45 times price. Okay? And so in this very simple regression model, whether it rains or not, you're just shifting your demand function up and down. It's higher for sunny days, it's smaller for rainy days. And you can see that in this plot. Okay? Just went ahead and plotted the 2 lines, and the sunny days are on top, the rainy days are on bottom. You can go ahead and do your calculus, right? Very simple. All you're doing is having a different y-intercept in the 2 models, and that gives you a different optimal price, right? So optimal price for a rainy day is smaller than an optimal price for a sunny day, right? And so we just have those 2 different lines. You get 2 different optimal prices. Okay, we can put temperature in along with rainy day, right? If it's cold and rainy, it's not going to be very good. Oh, and so we can go ahead and see this. You know, just put it in. You see that temperature, every degree of temperature increases on average your number of units being sold by 5. Okay, and if it's a rainy day, the number of units on average go down by 65. And so this is just the same as before if you think of temperature as just being part of the y-intercept. So as a function of price, the 44.2 plus 519 temperature minus 65 times rain, that's all the y-intercept as a function of price. And so we can go ahead and get the optimal price out. It depends on temperature and whether or not it's raining. Okay? And so when you look at that, here's the temperature. This is the optimal price versus temperature, and you can see as the temperature gets higher and higher, the optimal price for a sunny day goes up, and the optimal price for a rainy day goes up, right? And so, you know, that's how dynamic pricing would work. Okay. So just as a summary, if linear demand, this is, you know, if you, in Econ 101, you look at linear demand because your professors can draw it very easily and everybody in the class knows it. And you can get an optimal pricing function out where the optimal price is just halfway between the variable cost and where you hit the demand function hits the x-axis. And often it's very unrealistic in practice, right? For some of those estimation issues. 2 other popular demand functions, which you get in Econ 102 or real life, is log linear demand. And this gives a really nice formula for the optimal price. It's additive Markov. You just take your cost, and then you have the slope coefficient for price. Take cost minus 1 over beta 1, right? Again, beta 1 is negative. At least it should be for most products, okay? And then log is a little bit more sophisticated where you take log demand and log price. And in this case, beta sub 1 is called the price elasticity, right? The elasticity of demand to price, right? And then the optimal price is multiplicative. You take your cost, you multiply by a factor. That factor depends on the elasticity parameter. There's just one kind of fly in that ointment, we need beta 1 to be less than -1. Okay. If beta sub 1 is, let's say, -0.5, then you get a negative price, which doesn't work too well whatsoever. Okay. Well, that's all I have. I hope you enjoyed the video. If you did, hey, please give me a thumbs up, a like, and I hope to see you in video 2 and video 3 about dynamic pricing. So long for now.